Today's lesson is about enthalpies of formation. And as you can see the symbol right away, we've got an H and then we've got an F that comes after it. And that F is absolutely what we refer to as the enthalpy of formation. Okay, now enthalpy of formation is a little bit different. Normally when we talk about enthalpy, we talk about the enthalpy change of a reaction. Okay, when we talk about the enthalpy of formation, we're referring to the enthalpy change that occurs when 1 mole of a substance is formed from its elements. And when we say from its elements, we mean that it's literally how would you form that compound starting with just its elements. So you could write a chemical equation to show the formation of this substance forming from its elements. Okay, and we'll do some examples here in just a second of that. Okay, if a substance is already in its elemental form, such as sodium or xenon, or even O2, remember the diatomic molecules, Brinkelhoff, that each of those elements in their elemental form is therefore going to have an enthalpy of formation equal to 0. So if something's in its elemental form, then its enthalpy of formation is equal to 0. So, and that could be just an atom like sodium or xenon or any other element, or it could also be one of the diatomic molecules. Any of those are also in their elemental form, and so they have an enthalpy of formation equal to 0. Okay, so the first example here says write the equation that would represent the enthalpy of formation. Again, as soon as you see that, you've got to think, okay, I've got to form that compound from its elements. And so if we're talking about the formation of CO2, we have to form CO2 from its elements. Well, the elemental form of carbon is just C, and the elemental form of oxygen is O2. Okay, and that equation right there represents the reaction, the enthalpy of formation of CO2. And at the end, what we could do is we could write delta H equals, and it says it releases, so it's got to be a negative 393.5 kilojoules per mole. Okay, many times on the AP test, you'll see a reaction, and then afterwards they'll give you the delta H for that reaction. And if the delta H is a negative sign, like here, you know it's exothermic, it's releasing heat, it's hot. If the delta H is a positive value, then you know that it is obviously endothermic. Okay, so enthalpy of formation is forming a compound from its elements. So a third way that we can now calculate the enthalpy change for a reaction is to use the enthalpies of formation. Remember the first two, you take the value of Q, you divide by the moles, that gives you the enthalpy change. And then you take the bond energy of the reactants, you take the bond energy of the products, and remember this is a negative value, so you have that negative in there to represent that. You put them together, and you get the enthalpy change for the reaction. Okay, the third way that you can find the enthalpy change for a reaction is to take that epsilon there is the sum of, so we're going to take the sum of the enthalpy of formation of the products, and we're going to subtract the sum of the enthalpy of formation of the reactants. This equation is one of the equations given on the AP exam sheet, on the equation sheet, so you will have that available to you. Okay, this is where it starts to get a little bit confusing, because remember our second way of calculating the enthalpy change was to take the bond energy of the reactants, and then we took plus the negative energy of the product, so we subtracted the products. The bond energy one is the only time you ever go reactants minus products. We're actually going to learn a couple more equations this year, even in this unit, where from now on it is products minus reactants. Okay, and so we need to make sure we're clear on that the bond energy reaction to find the enthalpy change is the only time that you use the bond energy of the reactants minus the bond energy of the products. Other than that, your reactions are going to look very similar to this. Okay, let's look at example number 2. Example number 2 says calculate the enthalpy change for the reaction that occurs when propane burns in air, and when something burns in air, we know that it's reacting with O2. producing carbon dioxide and water. And then they tell us the enthalpy of formation of propane is negative 104.7. Then they give us the enthalpy of formation in CO2 was up here in problem number, or example 1. And the enthalpy of formation of water is negative 285.8. So one thing you might ask is, okay, well, first of all, let's write out our balanced equation. So we've got C3H8 plus O2 making CO2 and H2O. Okay, and now we do need to balance this equation. That the balancing is going to become an important component here. So we've got 3 carbons, 4 waters, 3 times 2 is 6, 6 plus 4 is 10, so we need 5 O2s. Okay, and now we know that in order to calculate the enthalpy change for this reaction, we're going to take the enthalpy of formation of the products. So our products are CO2 and H2O. And yes, we have to use the coefficients for the balanced equation. Remember that whole moles of reaction. Okay, if this is negative 393.5 is the amount of kilojoules per 1 mole of CO2 that's produced. Okay, well here we've got 3 moles of CO2 produced. So the enthalpy change for the reaction is going to equal the sum of the enthalpy of formation of the product. So 3 times negative 393.5 plus, now we're going to go to water, and there's 4 of them, so plus 4 times negative 285.8. Okay, and that's our products, minus the enthalpy of formation of the reactants. So it's products minus reactants. Well, one reactant is C3H8, and they tell us that that is negative 104.7. So watch what I do here. I've got products minus reactants, and so the reactants are negative 104.7. I'm just putting in exactly what they give me. And there's only one propane, so I don't multiply that number by anything. Okay, and then I go, and then I look, and I go, oh, I should go 5 times O2, but they don't give me any value for O2. And then I even ask you the question, why is the enthalpy of formation of oxygen gas not given in this problem? Is because, coming back up here, if a substance is in its elemental form, such as O2 or F2 or Na or whatever, then its enthalpy of formation is 0. So technically I could put 5 times 0 in here, but we know that that's just going to cancel out anyway. So I'm going to go ahead and just take that out of there and close my parentheses. And now I can get my answer. So I'm going to take 3 times negative 393.5 plus 4 times, and I'm typing it in the exact way I have it on my screen. So I did plus 4 times negative 285.8 minus, and then I'm going to do negative 104.7. And then I get a final answer of negative 2,219 kilojoules per mole. Now, is that a logical answer in terms of positive and negative? I'm saying that based on our enthalpies of formation, the enthalpy change for the reaction when propane combusts to make carbon dioxide water is absolutely a very, very exothermic process. And we can see that. It's negative 2,200 kilojoules per mole. So yes, absolutely, that negative has to be there. Anytime you have a combustion reaction, you're going to have a negative enthalpy change for that. It's always going to be exothermic. Okay? All right, example number 3 says write the equation to represent the enthalpy of formation of 1 mole of NaNO3. And that 1 mole means that when you produce NaNO3, you can only have a 1 right here. You can't change that number to anything else. And a lot of times what that means is when you write your reactants that you're going to have to use fractions. Maybe, maybe not. But when they say 1 mole, it means you can't change that coefficient in front of the sodium nitrate there. So We want to represent the enthalpy of formation, so we have to form NaNO3 from its from its elements again. So we're going to have sodium Na, and there's one of them, plus N. And now nitrogen in its elemental form is N2. Okay, and so that's why they're being a little bit sneaky there and saying, hey, we only want 1 mole of NaNO3. So I know it has to be N2, but I can only have 1 nitrogen on this side, so I do need to put a 1/2 in there. And yes, you absolutely not only can, you have to do that. If that's the way that they pose the question, that's what you have to do. Plus, and now we're going to have the same issue with oxygen. We know the elemental form of oxygen is O2 because, like nitrogen, it is a diatomic molecule. But I need 3 oxygens rather than 2 or 4. So again, here I'm going to use an improper fraction. 3/2 O2 is going to produce 3 oxygen atoms on the other side. Okay, and that's how you would write that equation. All right, now here, this page talks real quickly about enthalpy level diagrams. I like to look at these more in terms of something like this. Okay, where in this case, let's see, this one's actually an endothermic one, so let's draw it the correct way. Where typically I would see it more like that. Now, this part is true, though. For an endothermic reaction, as we can see here, here's the products, here's the reactants, here's the enthalpy over here. The enthalpy of the products here are greater. See how they're higher up on the table? The enthalpy of the products is greater than the enthalpy of the reactants. And then obviously the delta H is positive. Energy is absorbed. Again, nothing that you don't already know. Okay, in terms of exothermic, again, we know look like this. We know that, again, the enthalpy of the products versus the reactants, the enthalpy of the products is lower than, the enthalpy of the products is lower than the enthalpy of the reactants. Okay, so that's really all you need to know there. Now, many times when you see delta H, a lot of times they'll have the delta H and they'll have a little degree sign up in the corner. Okay, all that means is that means that you're at the standard state. And when you're at the standard state, what that means is all of the solutions or gases or whatever are going to be at the same conditions, okay? If you're at the standard state and it's gases, kind of like standard temperature and pressure, okay, but in this case, the pressure is just like STP. If they're gases, all of the gases will be at 1 atmosphere, okay? If you have a solution, which is more common here, if you have a solution, all the solutions will be, the concentration will be 1 molar concentrations. And here's where it's different from STP. Remember with gases, STP is 1 atm and 0 degrees Celsius. Okay, but the standard state with, again, pretty much everything else the rest of this year, when we talk about the standard state, the temperature is room temperature, which is 25 degrees Celsius, which is 298 Kelvin. Okay, so for example, the enthalpy of formation at the standard state is the enthalpy of formation, so forming something from its elements, at again 1 atmosphere of pressure or a 1 molar solution, and the temperature is at 298. Okay, now this we've talked about before, this diagram here. We do know that again, the reaction, the system is the reaction, and the surroundings are everything else. The beaker, the water, you know, if it's a gas, whatever container it's in, okay, things like that. And we know that if heat is going into the system, if the system, the reaction is absorbing heat, that's endothermic. If heat is exiting, if heat is being released, if the reaction is releasing heat, that is an exothermic process. Okay, we've seen that before. Okay, and I just talked a little bit about this. We talked about the enthalpy of formation. We've talked about enthalpies of reaction. Another enthalpy, which really you already know of, is also what we call the enthalpy of combustion. Sometimes you'll see it written like this, where they put just a COM on the bottom. And again, that represents combustion. That means something is burning. Now again, when something's burning, that usually is a very good giveaway that the reaction is releasing a lot of heat. So the enthalpy of combustion is almost always negative. Okay, again, I'm trying to think of an example when it's not, and I can't think of one off the top of my head. That enthalpy of combustions are typically not only negative, they're usually very negative. Now remember, what happens in a combustion reaction, if you're only talking about carbon, hydrogen, and oxygen, and they say air or something about air, you're not reacting with the air. Just like that previous example, you're reacting with O2. And more importantly, again, it doesn't matter what it is, you're always going to just produce carbon dioxide and water. So even if they say something like methanol, CH3OH, combusts completely in air, it reacts with O2, you're like, okay, it only has carbon, hydrogen, and oxygen in it, so my products are CO2 and H2O. Okay? What if it only has carbon and hydrogen and no oxygen, such as like ethane, C2H6 plus O2? Obviously, it's still going to produce CO2 and H2O because the oxygen is coming from the oxygen in the O2 at the beginning of the reaction. Okay, so this example here, we're going to write a chemical equation to represent the process that occurs for the standard enthalpy of combustion of C5H12. So if it says the combustion of C5H12, we know that's just going to be C5H12. If something combusts, it's O2, and again, it makes CO2 and H2O. Okay, what about carbon monoxide? Again, same thing. CO is going to react with O2. The combustion of CO, oh, wait a minute, there's no hydrogen in there. So are we going to make water with this? Nope, we've only got carbon and oxygen. So what's it going to make? It's just going to make CO2. Okay, I guess technically we should balance these. We've got a 5 there, a 6 there. That's 16 oxygens, so an 8 there. Here we've got 3 oxygens. Now we've got 4 on that side, so we put a 2 right there. Okay, what about hydrogen? What if the combustion of hydrogen would be H2 plus O2? And again, now this case, there's no carbon. So if there's no carbon, then it's just going to make H2O. So again, to balance that, we need that there. So if the substance if it has carbon and hydrogen, it's going to make CO2 and H2O. If it just has carbon and oxygen, then it's only going to make carbon dioxide. If it just has hydrogen and oxygen, it's going to make water. What if it doesn't have either one? What about the combustion of aluminum? Al plus O2. Well, any other element similar to this here, to hydrogen or carbon monoxide, is just going to be a synthesis reaction. So in this case, when you put aluminum and oxygen together, what do you get? Well, you get aluminum oxide. And aluminum has a +3 charge, oxygen has a -2 charge, so the formula would just be Al2O3. And to balance that, we need 6 oxygens on both sides, which means 4 aluminums on the other side. Okay, so a combustion reaction, again, depending on what is reacting, again, sometimes it's going to take some, not necessarily guesswork, but like on this one, you kind of have to just think about what is it that it's actually going to produce. And that's it for enthalpies of formation.